Welcome back, Design Junkies, to Mechanical Engineering Made Simple. We are diving into what I often call the great translation problem. You know, how do you take a genuinely vague, maybe hopeful customer wish and reliably translate it into a physical product that actually works, can be manufactured affordably, and crucially, won't fail catastrophically like a year down the road?
Right, and that whole process, that's really the heart of systems engineering, isn't it?
Yeah.
And today, our mission is really synthesizing best practices. We're not just talking about brainstorming here, but um, proven quantitative frameworks that actively minimize design risk, things that help avoid those structural flaws early on. We're basically building a foundational roadmap.
Okay, a roadmap. So it sounds like we're focusing on three big pillars that guide this whole translation effort. First, sounds like creating really airtight requirements.
Absolutely fundamental.
Second, structuring the solution using, well, you mentioned powerful frameworks like axiomatic design.
Yep, that's key for managing complexity.
And finally, applying something called critical parameter management, or CPM, to make sure that initial robustness survives the chaos of manufacturing.
Exactly. So let's start right at the absolute beginning, because honestly, if you mess up here,
The rest is just damage control.
pretty much, let's talk requirements.
Okay, defining requirements. Foundational. It feels like if your input here is fuzzy, your output is almost guaranteed to be shaky, right? These requirements, they need to capture the voice of the customer, which I guess usually comes out of a solid stakeholder analysis.
That's the ideal starting point. And you need clear, effective requirements.
So I want you, listening right now, to think, do your current requirements really meet these kinds of high-level standards we're about to discuss?
Well, they absolutely must meet several non-negotiable attributes. Okay, first, functionally.
Hmm.
They have to be verifiable.
Right.
That means you can actually prove, maybe through a test or some independent calculation, that you met the goal.
Okay, verifiable. Testable. Makes sense.
And they must be attainable. This just speaks to technical feasibility. Is it actually possible within the project scope, the budget, the timeline?
Right, and beyond just function, the clarity aspect is huge, isn't it?
Oh, absolutely. They need to be concise, short and to the point.
Oh.
And unambiguous. Everyone needs to read it and understand the same thing. But maybe the single most common failure point we see, especially in early stage design, it's violating the rule that requirements must be solution neutral.
Ah, the classic what not how principle. Easy to say, hard to do.
Incredibly hard sometimes. People naturally jump to solutions. If your requirement specifies, say, the diameter of a shaft or the material for a casing, you've started dictating the how. You haven't defined what the system needs to achieve. You've basically killed off potential innovation before the designer even, do the first line.
That's a really critical distinction. Confusing the need for some component with the actual functional requirement of the whole system, that seems like the root of so many early unnecessary constraints.
Exactly right. And the language, the semantics you use, carries that weight. This is where we talk about commitment. You absolutely must use the word shall for those quantifiable requirements. The things the system is contractually obligated to meet,
Okay, give me an example.
like the system shall weigh less than 3 kilograms, or the system shall provide a torque of at least 10 Newton meters. See, quantifiable, verifiable.
Got it. So if I see shall in a spec, I know that needs a test, a number, some kind of proof. What about other verbs like will or should?
Good question. If you're just setting the stage, maybe making a statement of fact about the context.
Mm-hmm.
Perhaps describing an operating scenario or the environment, you use will. Think like, the aircraft will fly at an altitude of 30,000 feet. That's context, not a requirement on the system being designed.
Okay, context versus requirement. And should, when does that fit in?
You use should really only for design goals, or maybe desired attributes where you just can't apply a strict, quantifiable, verifiable metric. It signals a preference, not a mandate. Getting that hierarchy right, shall, will, should, is absolutely essential for traceability, for verification, and for defining a solid product baseline.
Okay, so let's say we've done it. We have these crisp, solution-neutral requirements, shall statements locked down. Now, we've faced that massive challenge, translating those abstract whats into a physical system, the how. And this is where complexity just explodes, isn't it? We need some kind of framework, like axiomatic design you mentioned, to manage the chaos.
Exactly. Axiomatic design provides a structure. It helps map the customer wishes, which live in the customer domain, through the functional domain, what the system must do then, into the physical domain, how it does it, and finally the process domain, how you actually make it.
For this discussion, let's focus on that link between functional and physical.
Right. We're focusing on mapping the functional requirements, let's call them FRs, the what's to the design parameters, or DPs, the hows. So the FR might be the system needs to stop the car, and the DPs would be things like the diameter of the brake rotor, the material grade of the brake pads, the hydraulic pressure.
Okay, FRS mapped to DPs. And this relationship, you call it the design matrix. And it's governed by two big rules, or axioms. Axiom 1 feels like the really critical one for structure.
It absolutely is. Axiom 1 is the independence axiom. The fundamental goal here is to maintain the independence of your functional requirements. Basically, you want to avoid a situation where changing one physical thing, a DP, unintentionally messes up multiple functions, FRs.
Because if you link them all up in a complex, tangled way.
You've doomed yourself to what we sometimes call iterative hell.
Iterative hell, that sounds expensive and frustrating.
It's the guaranteed path to it. Because fixing one problem inevitably breaks three other things. It's endless cycles of redesign. So we strive for what's called an uncoupled design. That's the ideal. It's where each FR is controlled by only one unique DP. Think of a diagonal design matrix. Clean separation.
One knob controls one function. Simple.
Exactly. Now, if that's completely impossible, which it sometimes is in complex systems, we aim for the next best thing. A decoupled design. This is like a triangular matrix. Changes might still ripple, but they only flow one way. You can adjust things in a specific sequence without iterating endlessly.
Okay, so uncoupled is best, decoupled is manageable. What's the bad one?
The bad one is a coupled design. That's where changing a single physical parameter, a single DP, affects multiple functional requirements, multiple FRs simultaneously and often unpredictably.
But hang on, you mentioned complex systems. If axiomatic design demands this perfectly uncoupled diagonal matrix, isn't that sometimes just a fantasy? How do we actually use this when reality forces some coupling?
That's the brilliance of the framework. It doesn't just demand perfection. It forces you to recognize and manage the coupling you have. Take a simple example, like a refrigerator door. You have one key design parameter. Let's say the door's insulation thickness and seal quality. This single DP affects functional requirement 1, which might be provide reasonable access to the food, and it affects functional requirement 2, minimize energy loss.
Right.
They're coupled.
Right. Make the insulation thicker for better energy efficiency.
And you might make the door bulky, harder to open, reducing accessibility. You see the conflict.
Yeah.
An uncoupled or decoupled approach would try to find separate DPs to control those FRs independently if possible. Maybe different seal mechanism or vacuum insulation panels, something. Even if you can't fully uncouple it, the framework highlights the trade-off. It acts as a goalpost, constantly pushing you towards a simpler, more independent architecture. It makes the coupling explicit.
Okay, that structural clarity seems invaluable. It makes optimizing things later way more achievable. So axiom 1 is all about structural purity, independence. What about axiom 2? That sounded more mathematical.
It is. Axiom 2 is the information axiom. And the goal here is, surprisingly, to minimize the design's information content.
Minimize information? That sounds counterintuitive. Don't we want more information?
Not in this sense. Here, information relates to uncertainty. The more complex and uncertain a design is, the more information you need to specify it fully and guarantee it meets the requirements, the less likely it is to actually succeed. If we look at the formula, the system information content, let's call it I sub sys, it's inversely related to P sub m, which is the probability of meeting all the functional requirements. Mathematically, it's often written as I sub sys equals minus the sum from I equals 1 to m of log base 2 of P sub I, or simply I sub sys equals minus log base 2 of P sub m.
Okay, so maximizing the probability of success, P sub m, means minimizing the information content, I sub sys.
Precisely. A design where you have higher certainty about its performance, where the ranges are well controlled, it inherently has lower information content in this axiomatic sense, and it's mathematically considered a superior design.
All right, we've navigated the requirements. We've used axiomatic design to create a potentially brilliant, maybe even uncoupled conceptual design. Now comes the hard part, moving from that concept to execution, subjecting our idea to the harsh realities of detailed design, manufacturing, tolerances, the shop floor. This sounds like where we need that third pillar, critical parameter management, or CPM, to sort of protect our initial genius.
That's a great way to put it. CPM is all about maintaining the system's robustness, its ability to function correctly, despite variations throughout its entire life cycle. The goal is to make sure that those optimized values for the critical design parameters, the DPs we identified earlier, are actually sustained, that they flow down correctly, and are used to set the right manufacturing precision levels, the ones that ultimately guarantee customer satisfaction.
And you mentioned a key tool here, some kind of drawing.
Yes, the critical parameter drawing. Think of it as a special document that highlights only those few parameters that are absolutely critical for the core function and robustness identified way back in concept selection.
How does it act like a beacon, as you put it earlier? What does it protect against?
It protects against the natural tendency for detailed designers to get lost in the weeds. And I say that with respect. Their job is incredibly complex. They're focused on, localized safety factors, specific manufacturing processes, minimizing the cost of this bracket, ensuring that component can be assembled easily.
Right, lots of local optimizations.
Exactly. And in that intense focus, it's incredibly easy to accidentally compromise one of those original critical functional requirements. Maybe it was ensuring a specific belt tension stays nominally at 15 newtons, plus or minus very little. The critical parameter drawing cuts through all that other noise. It keeps everyone's attention focused on those specific values that are essential for the robustness of the original technology choice. It says, whatever else you do, don't mess this up.
This whole issue, balancing precision with cost, it feels like the foundational struggle of modern manufacturing, going back centuries. You can trace this obsession with tolerances way back, right? Late 18th century, Gribeauval in France trying to get interchangeable musket parts.
A dream only really realized much later by people like Henry Ford with his assembly lines and his intense focus on gonna-go gauging and tight tolerances.
But that obsession just kept driving costs up, didn't it? Just making everything tighter and tighter.
It did until Dr. Walter Shewhart gave us the crucial insight we needed back in the 1920s at Bell Labs. He realized, through statistics, that we must distinguish between two types of variation. There's the natural inherent variation in any process, what we characterize using standard deviation, sigma, and then there's variation caused by specific, assignable, or special causes, a broken tool, a bad batch of material, etc.
And that distinction is key.
It's everything. Shewhart gave us control charts, the tool to stop chasing ghosts, the inherent random variation, and focus our efforts only on fixing the real special cause problems. It fundamentally changed quality control.
Okay, so that statistical understanding leads directly to the core economic choice we face today. How tight should our tolerances actually be? Because making things more precise always costs more money to manufacture.
Right. The optimal decision from an economic standpoint is the one that minimizes the total cost. And total cost is the sum of two things: the manufacturing process cost and the quality loss that occurs downstream due to variation from the target value.
Quality loss, meaning failures, customer dissatisfaction, warranty costs.
Exactly. And this brings us to the concept of three-tiered tolerances, which is directly tied to Dr. Taguchi's quality loss function.
Let's break that down conceptually, because this feels like where the real money is saved or lost in production.
The key insight from Taguchi is that quality loss doesn't just suddenly appear when you hit a tolerance limit. It grows quadratically as you deviate from the ideal target value.
Quadratically, meaning if you're twice as far from the target.
The loss isn't just double, it's 4 times higher. 3 times the deviation, 9 times the loss. It ramps up fast.
Wow.
The expected quality loss, let's call it L, is proportional to the square of the deviation, delta squared. So the basic relationship is L equals some constant times delta squared.
Okay, so how do the three tolerance tiers fit into this?
Right. First, you have the customer tolerance. Let's call it delta sub C. This is the deviation point where the average customer becomes dissatisfied. Maybe the product feels noisy or it fails prematurely. Hitting or exceeding this incurs a massive quality loss, L sub C. Think expensive field costs, recalls, brand damage, huge numbers.
It's a cliff we absolutely want to avoid out in the field.
Exactly. Now, back in the factory, we have the manufacturing tolerance, delta sub M. This must be much, much smaller than delta sub C. Why? Because the cost of countermeasures inside the factory, let's call it L sub M, is vastly cheaper. We're talking about scrap, rework, maybe sorting parts. Much less expensive than a field recall.
So we set a tighter tolerance in the factory because fixing problems there is cheaper. How do we calculate how much tighter?
We use the quality loss function to balance those costs. The full formula for expected loss is L equals L sub C times the ratio of, open parenthesis, delta squared, close parenthesis, divided by, open parenthesis, delta sub C squared, close parenthesis. And to find the optimal manufacturing tolerance, delta sub M, where the cost of fixing it in the factory, L sub M, equals the expected loss if we shipped it. We calculate it as delta sub M equals delta sub C times the square root of, open parenthesis, L sub M divided by L sub C, close parenthesis.
Okay, let me repeat that back slowly. Delta sub M equals delta sub C times the square root of the ratio of L sub M over L sub C.
That's it. That formula gives you the rational economic boundary for your manufacturing tolerance. It tells you, based on the cost of failure in the field versus the cost of fixing it now, whether a part should ship or be reworked. It's pure economic optimization based on that quadratic loss.
We've covered structural rigor with axiomatic design, economic control with CPM, and the quality loss function. But the whole process is still driven by human creativity, right? And increasingly by our reliance on really complex simulation tools, computer-aided engineering, CAE. So how do we ensure our innovative thinking is actually effective? And maybe more importantly, how do we make sure we don't just blindly trust our complex computer models?
Great questions. On the innovation front, it's useful to contrast conventional design thinking with approaches like TIZ, the theory of inventive problem solving. Conventional thinking often defaults to finding a compromise, balancing competing requirements. TIZ, however, is guided by something called the law of ideality, which observes that technical systems tend to evolve towards being more reliable, simpler, more effective, more ideal over time. TIZ provides tools and principles to actively overcome technical contradictions without making those compromises. It's a different mindset.
Aiming for the ideal, not just the acceptable compromise. That philosophical shift seems powerful.
It is. And that drive towards ideal solutions often pushes us towards heavy reliance on CAE, on simulation for verification and optimization. Which brings us to your second question.
Trusting the models. Because let's be honest, simulations can be wrong.
They absolutely can be. And sources consistently point out that poor answers from simulations are, frankly, tragically common. It could be bugs in the code, it could be physical effects the model doesn't even include, or just garbage in, garbage out with inaccurate input data.
So this raises a really critical question. When engineers are using these sophisticated models, maybe doing parameter design studies to optimize something, what's the best strategy, not just for optimizing, but for actually detecting if the simulation itself is flawed?
And the research on this yielded a fascinating and highly counterintuitive result.
Okay, I'm intrigued. What did they find?
Well, a study was done comparing engineers using different strategies for parameter design, specifically looking at their ability to detect underlying flaws deliberately hidden within the computer simulation model they were using. One group used complex, statistically designed experiments, DOE, the multi-factor orthogonal array type stuff, the gold standard for efficient optimization.
Right, the methods we spend a lot of time teaching engineers.
Exactly. The other group used a much simpler approach, adaptive one factor at a time, or OFAT, basically just changing one variable, seeing what happens, changing the next, the old school way.
Okay, so intuition says the complex DOE method should be better, right, more systematic.
That's what you'd think. But the goal here wasn't just optimization efficiency, it was flaw detection. And the results were, well, shocking.
Don't keep me in suspense.
The engineers using the simpler adaptive OFAT method were significantly more likely to detect the hidden flaws in the simulation.
How much more likely?
The detection rate for the adaptive OFAT group was 52%. 52% of them found the flaw.
Okay, and the complex DOE group?
Only 4%.
Wait, what? 52% versus 4%? That's almost unbelievable. We push these complex methods, and the simple, one-step-at-a-time approach was over 10 times better at catching bugs in the model.
That's what the study found. The interpretation is that the very complexity of the designed experiment strategy might actually mask the unexpected behavior caused by a flaw. When you change multiple things at once, it's harder to notice when the system response is just weird, off. Doesn't make sense.
Whereas changing one thing at a time makes anomalies stand out more clearly. You have a simpler expectation to compare against.
Precisely. So the key takeaway here for you listening is profound. Sometimes simplification of your search strategy actually makes you more capable of perceiving those hidden critical errors, especially in complex computer simulations. It's a crucial human insight that complements all the sophisticated mathematical and structural tools we've discussed. We are simply better flaw detectors when we simplify the immediate test environment. Hashtag tag outro epro. So when you pull it all together, success in complex systems design really hinges on a combination of things. It requires structure, enforcing absolute clarity and solution neutrality in requirements, using frameworks like axiomatic design to strive for that uncoupled architecture. It requires vigilance, applying things like critical parameter management to maintain robustness through the manufacturing process, and maybe most critically, recognizing the human element. Understanding that sometimes simplicity in our testing approach is what allows us to perceive the flaws that complex methods might obscure. Structure, vigilance, and simplicity.
It really is fascinating, isn't it? After diving into these high-level concepts, the design matrix, quadratic quality loss, economic optimization, we circle right back to the realization that sometimes our most reliable defense against potentially catastrophic design flaws isn't some super complex analysis, but maybe just the most basic one factor at a time test done thoughtfully.
Indeed. And perhaps that leads to the final provocative thought for you to take away and explore. In a world filled with increasingly complex, interdependent systems, how can you structure your next technical challenge, your next design problem, to ensure that the simplest possible test case has the best chance of revealing the most critical flaws?